The next topic we're doing is frequency response. And frequency response is basically finding the poles and zeros in your circuit to see whether a signal of a certain frequency will get through your circuit, or whether it be attenuated, or whatever might happen. So again, finding poles and zeros. If you look at a circuit like this looks like an extremely complicated circuit. This is a 555 timer, so it has a couple of things that you won't see in analog circuits. For example, you've got inverters over here. You've got cross-coupled inverters, and remember, a cross-coupled inverter is a memory cell. And those that have done 555 timers, you know there's an RS latch. So this is probably part of the RS latch over here. But yeah, this is a really complicated circuit. And you say, like, oh my goodness, where do I start? Turns out that you will have a pole between every stage. So in the last couple of classes, we've been looking at some pretty complicated amplifiers, off-the-shelf, professionally designed, products, actual amplifiers that are being sold for money. and you've looked at them and you can see all the different parts. But the first stage of doing that, of looking at a complex amplifier and trying to figure out what it's doing, is to divide the amplifier into stages. And it turns out that between each stage, you have a pole. So that's the first thing. So that way, it's kind of simplified the problem quite a bit. In between each stage, there's a pole. The other thing is that on gain stages, you'll have a zero. And that zero, we're going to have to do small signal analysis with a small signal model that has that we will add capacitors to. So we'll add capacitance to the small signal model, do small signal analysis to figure out where a zero is. But once you have that equation for where a zero is, it's kind of like, when you have R pi, R pi equals beta VT over IC. So you know the equation for R pi, so you don't need to recalculate it every time you need to figure out the value of R pi. Same thing for zeros. Once you do that small signal analysis and figure out the equation for where the zero is, you can just use that equation and you don't need to recalculate every time. We'll use small signal analysis with a model that's a little more complicated than the model we've been using. Basically just has capacitors added to it. We'll memorize an equation for the zeros, and then we just know that every gain stage has a zero at a particular point, and that greatly simplifies it. Okay, so why do we have poles between each stage? Let's look at, let's find this. So T24, it's not really, actually there's some cross-coupling going along here, but let's pretend T26 and T24 is a common source with an active load. So let's say this is the input. Again, this is a flipped common source with active load. T24 is the active load. And what happens is when you have a stage, you change the input to that stage. If it's a common emitter, you change V in, and then the output of that stage, V out, would change. Okay. And when you're changing the voltage at a node, so looking at the output of the stage, when you're changing a voltage at this node, what you're doing is you're charging up or discharging capacitance. Okay. And let's see. That's not what I was looking for. Okay, so when you, sorry, I thought I had it paint up. When you are looking at the charging up a node, this is just the basic capacitance equation. If you have a voltage across a capacitor, so think of a parallel plate capacitor. And you have the second plate here. When you have a parallel plate capacitor, the voltage between these two is actually the difference in charge between these two. So if you have a million electrons here and you have 2 million electrons here, then you have a difference of 1 million electrons. So Q you can think of as that difference in charge. And capacitance is how close these are, how big the field is between these two plates. That's a little bit wrong definition, but this is the basic capacitance definition. If you take the derivative of both sides with respect to time, assuming C is constant, you get this, and dq dt, the change in charge per unit time, that's flowing charge, that's just your current. And what you can see here is how fast a node changes. So the change in voltage per unit time. So how much the voltage changes in 1 second equals I over C. That's just massaging this equation, dividing both sides by C. Okay. So how fast a node changes is how much current divided by how much capacitance is at a node. So what you can do here is you have, which one was I using? I was using 26 and 24. So right here, let's say the input to 26 changes, this output will change. There's a bunch of capacitance on this node. Generally in LT-Spice or probably the other simulators you've used, you've treated this as an ideal wire and maybe not even thought about capacitance. But the wires contribute capacitance, transistors contribute capacitance, that wherever this is connected to contributes capacitance. So there's actually a bunch of capacitance on this node. It's not explicitly drawn into the figure. It's parasitic. In other words, you don't want it. Be nice if it wasn't there, because then this node would change infinitely fast. But there's capacitance on this node. And then you have this transistor here that charges up this node, means the current goes through T26. T26 cannot conduct an infinite amount of current. It limits the current, so it's behaving like a resistor. So let's see. So this node right here, it's getting charged up through something that looks like a resistor, and this node has a bunch of capacitance. So what this looks like is what every node between every stage, what it looks like is if you're charging up, this would be the output of your amplifier. This would be the supply or ground. The input just controls whether you're charging up or discharging this node. But this, what happens is this is either VCC, and this is your V out of that node, of that stage. So if you have a stage, you have V in, which controls whether you're charging up or discharging. You have the supply, you have the ground, and then you have V out that has some capacitance on it. And that capacitance is either getting charged up. If V in is telling the top half to conduct, then V out's getting charged up. Or if V in is telling this node to discharge, then there's going to be a path down to ground. So it all depends what V in is, whether it's charging up the capacitance or discharging the capacitance. But either way, these transistors limit the current and behave like a resistor. So if you look at this circuit right here, you think back to 211 maybe, of what this circuit is. This is a low pass filter. Low pass see if this has come back yet. Oh no, no pen. Filter. Which means that when you are putting a low frequency signal through your circuit, it gets through just fine. The signal has time to get through to the output of your stage. Get through to the output of your stage. No problem. All intact. From basically a gain of 1. But as your input signal goes faster and faster, eventually you get to a point here, and the corner is at the omega corner is 1 over your RC. And that's the frequency where it starts to attenuate the signal. And if you get too much past that, then your signal basically disappears. So, yes, so what we're going to look at next is how to find R and how to find C.